Good afternoon and welcome to The Power of the Snake, Number Theory with Python. Our presenter today is Markus Reitenbach from Colorado Mesa University. If you have any questions for the presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom screen, and we will address them at the end of the talk. And on that note, I'll hand it over to our presenter. Markus, I think you're on mute if you have started.
Let me unmute. Okay, can you hear me now?
Yes. Yes.
Okay, very good. I'm trying to get screen sharing going, but okay, I can't share the entire screen, which is fine. I'm just sharing some individual windows now. Yeah, so I'm actually presenting a paper that was published last year. You see that right here, and also the abstract. So I don't think I have to say anything more about that. Now let's see. Let me share another screen now. Okay, sorry about that. It's always a little difficult with Zoom. So yeah, let me talk about Python, and then I'll show you some code examples. So Python is about 30 years old as a programming language, and it has become more and more popular over the years. And there are several reasons for that. It's just very easy to use, very intuitive, not very technical, and it lends itself very nicely to do number theory. So let me first show you how to use Python as a calculator. And I hope you guys can see my screen here. You see on the left the heading Python as a calculator. Does everybody see that?
Yes.
Sorry, I don't.
Yes.
Yes, thank you for the feedback there. Yeah, so Python is an integer calculator. So if I try the 22 and then divide it by 4, not the usual division sign, but the double slashes, it gives me just the quotient as an integer. So not 5.5, but 5. And maybe somewhat more interesting would be 22, and then the percentage symbol is the modulo operator. So that gives me the remainder when I divide 22 by 4. So in other words, I'm reducing 22 modulo 4, and that's of course 2. And one cool thing about Python is that there is no limitation on the size of integers. So if I do this command, it raises 333 to the power of 333. And you see, if I press enter, the result is almost instant, and it won't complain that the number is too big or anything. I could even give it something like the power of maybe this number to this even larger exponent. Now, if I did this, it would, of course, run forever. I mean, it wouldn't terminate because the number is just too big. But if I do that, let's say mod 4, so I just add the comma, it reduces the output mod 4, or in other words, it does the arithmetic modulo 4, and that's almost instant. So here it happens to be 1. Yeah. So this is, of course, implemented with binary exponentiation algorithm. So when I teach number theory, I always teach that binary exponentiation algorithm, and then I show them how the students can do it in Python, and they're really surprised how fast it actually is. Okay, so let me move on to lists. So lists can be very easily defined in Python. So let's say I want to define a list called squares that has these elements. So I just put that in, and then I can access the entries of the list by using the bracket notation. Now, squares of 3 gives me the third element in the list. And the third element in the list is actually 9 now. That may be counterintuitive. But Python actually always starts counting at 0. Yeah? So the 0th element is 0, the first element is 1, the second element is 2, and the third element is therefore, sorry, sorry, I think I misspoke. The second element is 4, and the third element is 9. Even nicer is a feature that's called list comprehension. So let's say I want to define a list of a few cubes that are, let's say, just powers of the first few integers. So power of I, 3. So those are cubes. And now if I say I is in range 6, that means I goes from 0 to 5. So again, Python counts starting at 0. So the first 6 numbers when I start counting at zeros are the numbers from 0 to 5 inclusive. So I can, let's say, just loop through the elements of that list now to see what they are. So I'll do that next. Yeah. So now I'm looping through the elements of the list cubes and print each element. And you see what I get. I do get actually those cubes that I just created. Yeah. So looping through a list is also a very nice feature in Python. Okay, so last thing before I actually talk about number theory stuff is functions. And functions are also very easily defined in Python. So this function here simply defines a function cube of x that returns the cube of any input that I give it. Yeah, so the cube of 7, of course, would be 343. Okay, let me maybe clear that screen a little bit so we can keep going. So the first substantial result in number theory is arguably the Euclidean algorithm. So let me show you this piece of code. I'm going to run this real quick. And so basically what it's doing, it's not just the Euclidean algorithm, but it actually gives you the GCD, and it also expresses the GCD of two numbers A and B as a linear combination of the inputs A and B. Now, so without looking at the code, let me just show you how it runs. And you can also see that up here, this symbol is the comment sign. Yeah. So that function returns a triple gxy such that x and y are the coefficients when you write the greatest common divisor as a linear combination of the inputs. So for example, the extended GCD of 20 and 12, it will return the triple 4, -1, and 2. So 4 is the greatest common divisor, and that number 4 is actually -1 times 20 plus 2 times 12. Yeah? So now, if you look at the code, it's actually quite simple. The first few lines just deal with special cases, and then in the last 2 lines, I am really just implementing the Euclidean algorithm in a recursive manner. And for a student who hasn't taken programming, this probably doesn't make sense, you know? But it's not a big deal, because the point is the students can use that. Yeah? So students can use that where the inputs are large numbers with, let's say, hundreds of digits, and the output, I mean, the result will be there almost instantly. So the lesson that students can learn from that is that the Euclidean algorithm is extremely efficient. Okay, Python can also do modular inverses. Yeah? So if you maybe just look at the left, I implemented the function mod inverse of a comma m by simply evoking the extended GCD function. I mean, basically, to find the modular inverse of a mod m, we are expressing 1 as a linear combination of a and m to get that modular inverse. So it's, again, very simple. And there is even a better way, namely, since Python 3.8, you can find the modular inverse with that power to the -1 notation. So if I do, for example, power of 2, -1, 5, that basically gives me the inverse. So the -1 stands for inverse, right? So in other words, 2 to the -1 mod 5. Yeah? And of course, the inverse of 2 mod 5 is 3, because we all know that 2 times 3 is actually equal to 1. Well, at least modulo 5, it is 1. Okay, let me keep going. The last example of code I have here is the Chinese remainder theorem. And let me maybe just run that real quick so I have it available. Okay, and you see this is a bit more involved. But in some sense, it's still pretty short. So if you look at the comment section, it kind of explains what it's doing. So the inputs A and M are not numbers, but they're actually lists. And in fact, the A's are a list of moduli, and the A's are a list of right-hand sides of congruences, and the M's are lists. The M is a list of moduli. Yeah. So to give you a very concrete example to make this maybe more clear. If I pass it 2 lists as arguments, then 1, 2, 3 are the right-hand sides of congruences, and 7, 8, 9 the moduli. Yeah. So in other words, this solves the system of 3 congruences, where the first congruence is x congruent 1 modulo 7. The second congruence is x congruent 2 modulo 8. And the third congruence is x congruent 3 modulo 9. Yeah? And well, 7, 8, and 9 are, of course, pairwise coprimes. So there is a unique solution modulo the product of 7, 8, and 9. And that solution is 498. Yeah? And if you look at the code, it's actually very short. It's only 6 lines of code. And if you analyze that, it really just follows the standard procedure of constructing a solution for a set of simultaneous congruences. And I should say that for sake of brevity, I did actually maybe not check a few things. I mean, to make this a proper programming style, I guess I should have maybe checked that the moduli are pairwise coprime or prime or something to ensure that the solution exists. Yeah. So, and also I'm not outputting all solutions, but only the unique solution modulo the product of the moduli, which is the capital M here at the very end of the code. Yeah, so that's it for my code examples. I should point out that I used this in 2 of my classes. I used it in a number theory class, and then I also used it in a cryptography class. And it was generally quite well received by the students because they really seem to have fun playing with this. And I usually don't give them programming assignments. I usually just give them the code and let them play with the code, let them figure out how fast certain algorithms are or how slow certain things are. And it seems to really help them understand what the power of number theory is, especially when it comes to applying number theory to cryptography. Now, if you wanted to give your students programming assignments, you can certainly do that. So, for example, you can ask your students to write a function solve congruence that has inputs A, B, and M. Yeah? And I guess what that would do is it solves the congruence AX congruent B mod M, if there is a solution, or it maybe says, okay, there is no solution. Yeah? And doing that is, again, very easy because all you need to do is you need to call the extended GCD function or maybe the modular inverse function to solve that congruence. Yeah. So if you wanted to make this an assignment, I mean, that would be an assignment that students who have some programming experience actually should be able to do. Okay, let's see. I should maybe point out that much of this code is available. So let me maybe change to another window now for sharing. So when I taught these classes, I just kind of, wrote the code piece by piece and, gave that to my students, had them play with it. Let's see, let me share a window now. Do you guys see the GitHub, the Python, the GitHub window now? Do you see that?
I'm gonna say
Yes.
yes again.
Yes.
Yep, you see that? Okay, great. Yeah, if you want to use some of my code, feel free to do so. I put it on GitHub, so it's all there. I even put some instructions on how to run Python code. And you see, I have a few utilities. Actually, the first one is obsolete. The product of a list of numbers is now part of Python. We don't even need that anymore. So I showed you the extended GCD, the modular inverse. The congruence solving would be a good assignment. There is another one for solving Diophantine equations, which is useful, of course. I did implement the Miller-Rabin prime test, and the students are always surprised with how fast that runs. I mean, if n is a number with 200 digits, it literally takes like a microsecond or so to test that number for primality. I have functions for prime generation. I have functions for factoring numbers, listing prime factors, that kind of stuff. Of course, the Euler-Toscan functions, checking whether a number is a primitive root or constructing a primitive root of a number. The order of A mod n is kind of nice and useful, might be even useful for an abstract algebra course, stuff on hashes. And then for my cryptography class, I implemented various crypto schemes like the RSA, as you can see here, the El Gamal crypto scheme, the Pauling-Hellman algorithm. Well, that's just to find discrete logarithms, and that's a hard problem, of course. And maybe let's look at the last one. Yeah, I also have some tools for elliptic curve computations. Yeah, like so the students can kind of get a feeling for how the addition and multiplication of points on the elliptic curves actually works, and yeah, finding the order of a point, finding generators, all these kind of things. No? Yeah, I think that's about all I wanted to say. So maybe I should open it up for questions now.
I have a quick question. Can you show again the list of functions that you just showed on the number theory?
Oh, absolutely, yeah. Let me share it again.
I didn't catch all of them. I just want to go.
Oh, yeah, sure. And by the way, if any of you wants any of this, I can email you my paper, the paper that was published last year, and the paper has the link to my GitHub website, so you can access it easily that way. So if you just send me an email, I'm at Colorado Mesa University, or send me a private message once I'm done talking, I'll share this with all of you. So back to these functions. Sorry, I'm a little bit slow here. Yeah, go ahead.
Oh, thank you, Markus. One of my colleagues is actually teaching a Python class. So I'm going to send an email to you for the information and probably CC him on it, because I'm sure he will appreciate having more resources.
Oh, absolutely. So is that visible now, that the GitHub screen?
Yes.
Can you guys see that? And you wanted to see the which ones? I mean, there's basic utility.
Basic number utility. Yeah, those are. Yeah, just want to make sure I didn't miss any of them. Great, thank you. Yeah. So and I'll look you up in GitHub. I'll look it up.
Yeah, exactly. Just look me up at Colorado Mesa University. Send me an email or something. I'm happy to share my paper on the GitHub. Yeah.
Great. Thanks a bunch. Thank you. Thank you.
Yeah, you're welcome.
Hi, I can ask one question. So these same things that you have done for Z, can you do this on Python on some higher number fields as well?
On some what? So sorry?
On some number fields, like higher degree number fields?
I would think I'm actually not. That's not my area of expertise. So
Okay.
I think I don't know too much of the mathematics, but Python is very conducive to any kind of coding that is not too close to the operating system and it doesn't rely on hardware things. So it is very, very good for this kind of stuff.
Thank you.
Thank you again, Markus.
Yep, you're welcome.
All right. Well, if we don't have any further questions, we'll go ahead and wrap up. Thank you, Markus, for all that valuable information you shared with us today. The next session will begin in 6 minutes. You can view the chat for the session meeting room links or access the conference website for a complete list of sessions and their descriptions. While accessing the conference website, don't forget to swing by the virtual booth to say hello to the Hawks team. Do a quick 5-minute demonstration and you'll be entered to win a $50 Amazon gift card. And we'll see you all at your next session.